And we will end with the most recent news from the lasers station. And we welcome Sagie, who's currently a PhD student.
Thank you. Okay, I'm Sagie, and today I will give you an overview about our recent investigation of non-Hermitian physics with coupled lasers. Feel free to ask me questions whenever you want, but remember that I'm the only thing that stands between you and dinner. So take this into account. Okay, so but before getting to the physics, let me introduce you to our experimental setup, which allows us to create many lasers, to control them, to couple them, and to create this crazy laser beam like this Newton beam. Okay, so our setup is made of two mirrors and two lenses in a force configuration. Now this force configuration means that every ray that emanating from the right mirror will return to itself after the round trip. So if we add a mask with 1,000 holes next to the right mirror, we get 1,000 independent cavities. So because the light that comes out of each of these holes returns to itself after the round trip. So by adding again, we get 1,000 lasers. This is an image from the lab. And when we look at its far field, where all the lasers interfere, we see this wide Gaussian, which means that the lasers are incoherent and these are indeed independent lasers. So to make things interesting, we couple the lasers. We do that by sending light from each laser to the neighbors, and so we do it by displacing this mirror, and then each laser propagate a bit, and the tails lead to the neighbor, and then now the phases of the lasers matter, and they phase lock. They phase lock and give this far field pattern. Now these sharp peaks indicate on long range coherence, and this central peak here is 1,000 times stronger than this wide Gaussian in the case of uncoupled lasers. Okay, so this is a more fancy illustration of our setup, where we replace the mask of holes with a spatial light modulator. This is an expensive digital mirror with 2 million pixels, and we can control the phase of each of them. So it allows us to generate digitally any array geometry that we'd like. It also allows us to control the resonance frequency of each of the lasers, and also the loss of each of the lasers very accurately and independently. Also, as I said, we couple the lasers by shifting the mirror, so the amount of displacement determines the phase that the light accumulates when it goes from one laser to the other. So it's also a very accurate knob over the coupling strength and phase. Then we image the lasers, of course, we look at its near-field intensity distribution and also the far field. But the thing that I want you to remember for the rest of the slides is that we can generate lasers in whatever geometry. We can control the resonance frequency, the tuning, delta omega, the loss, delta alpha, and the coupling phase. This is what you need to remember. Okay, so now let's understand what do I mean by non-Hermitian. So you all know Hermitian Hamiltonian. They describe isolated system where energy, particles, probability are conserved. These Hamiltonians have real spectrum and orthogonal eigenmodel. This is an Hamiltonian, for example, and it can describe two coupled waveguides. Now you all know the behavior of such a waveguide. You inject light to one of them, and it just oscillates back and forth between the waveguides with the same average amplitude in both. Okay, now open systems that do exchange particles, energy, probability with the environment are described by non-Hermitian Hamiltonian, and these in general have complex spectrum and their eigenmodes are not orthogonal, like this Hamiltonian, for example. In this Hamiltonian, it also describes coupled waveguide, but now one waveguide experiences gain, delta alpha, and the other experiences loss of delta alpha. Now, this is a special Hamiltonian because it obeys a special symmetry, which is called the PT symmetry or parity time symmetry. And that means that if I act with the parity operator on it, and then with the time reversal operator, I get the same Hamiltonian back again. And let's do it together because it's really easy. If I act with the time reversal operator, gain turns into loss and loss into gain, so the minus comes out. And then when I act with the parity operator, I just switch between the two waveguides. And then the minus comes back down and I get the same Hamiltonian. So this is a pretty symmetric Hamiltonian, and that means that it has a completely real spectrum. And here I show the imaginary part of the eigenvalue as a function of the detuning, and you can see that as long as delta alpha is smaller than kappa, we get an entirely real spectrum. And one of the really cool things here is that now no matter where we inject the light to which waveguide, it will oscillate back and forth very similarly to the Hermitian case. The average amplitude in both waveguides will be exactly the same, although one experiences gain and the other loss. So now, if we increase the coupling, the loss to be larger than the coupling, then we get to the PT broken phase, where the waveguides behave as we would expect. We inject light to one of the waveguides, and then it goes to the amplified one, and then get amplified exponentially. Now, in between these two phases, the PT symmetric phase and the PT broken phase, we have a special point, which is called exceptional point. This is a special degeneracy in which not only the eigenvalues are degenerate, but also the two eigenmodes become identical. It can happen only in non-Hermitian Hamiltonian. And as you can see here, the system is very, very sensitive to perturbations around this point. And this made such systems very, very attractive. And so there are many, many works that are trying to demonstrate PT symmetry on many systems and to harvest the sensitivity of the exceptional point for very sensitive sensors. Okay, so now comes our contribution. So, as you may notice, in order to get to the exceptional point, we need to go over the PT symmetry line. The two waveguides must have exactly the same resonance frequency. Any small detuning between them, delta omega, will just kick you out of this PT symmetry line, and then we won't get to the exceptional point. So this is the PT symmetry line in this parameter space of loss and detuning, and we showed that actually this PT symmetry is a special case of a more general symmetry, which is called the Anyonic-PT symmetry. Okay, so this is a more general Hamiltonian. Don't be scared, it's exactly the same. I just added now a detuning between the two sides. And so we showed that if you go along a line, which is rotated by an angle beta in the parameter space, then you can get to an exceptional point by adding a phase to the coupling and the phase should be exactly the rotation angle of the line in this parameter space. So if you walk along this line, you will get an exceptional point. And also, if you walk along this line, your Hamiltonian is Anyonic-PT symmetric. Now, we went to the lab, this time with two lasers, not with two waveguides, and these are experimental results. You can see that this is the amplitude ratio of the two lasers as a function of the relative detuning. Now remember that we are going along a rotated line in this parameter space, so when I add detuning, I also add loss. So you can see that in the Anyonic-PT symmetric regime, we get the same amplitude exactly to both lasers, although one experiences gain and tuning and the other experiences the opposite thing. Then we get to an exceptional point, which goes like a square root, and then we get to the Anyonic-PT broken phase. So it's not luck. We repeated the experiment along different angles in this parameter space, and changing the beta, the coupling phase, accordingly. Okay, so you can also recognize this square root, which shows the sensitivity of the perturbation around the exceptional point. Now, these 1D diagrams are actually a cross-section of more complicated phase diagrams, two-dimensional, but I don't have time to speak about them. I just say for the experts that we show that in two extreme cases, where the coupling phase is zero, in order to phase lock the lasers, we must insert the tuning between them. They won't phase lock if they will be exactly on resonance. And in the other extreme, where the coupling is purely dissipative, where this line is rotated by pi over 2, in order to phase lock the lasers, we can phase lock the lasers beyond the critical detuning by adding relative loss between them. However, if someone didn't understand, I hope you enjoyed the nice colors. Okay, so now to the next topic that you work on, in which we show that we can induce chiral states using complex potential. So usually, if you have a network of oscillators and you want to induce some chiral edge states or chiral bulk state, you will use some kind of asymmetric coupling, like magnetic field, artificial magnetic field, or other types. But there are many systems in which asymmetric coupling is just not available, like our symmetrically coupled lasers. Now, so we showed that if we add a complex potential, we can get this almost pure chiral state, and it's really easy to implement. It can be applied to various network geometries, to various physical systems, even like human networks that Moti showed, and it's easily scalable. So to demonstrate the idea, we chose a triangular lattice of lasers, which has the degenerate lasing mode. The two lasing modes have opposite chiralities. In one case, we have the staggered vortex, and in the other, the staggered anti-vortex. Now, each time that we turn on the lasers, we get one of these modes with equal probability. So, so we say that we have no chirality on average. So the idea of complex potential is the following. We take two lasers in each triangle on the triangular lattice and apply a small detuning in between. Then we apply a weak loss to the third laser, and we do it self-consistently throughout the array. Now, the term complex potential comes from the fact that these detuning and loss terms are on the diagonal of the effective Hamiltonian of the system. So when we analyze the Hamiltonian, we see that we can, this is the chirality of the system, of the minimal loss eigenmode of the system, as a function of the detuning in units of loss, and you can see that we can get really pure chiral peaks if the detuning and loss are approximately equal. These 2 points are very special. Can you guess what those are? Good. These are exceptional points. At this point, the system collapsed, the Hamiltonian collapsed into either vortex mode in this case, or to the anti-vortex mode. This is the only available state of the system, therefore we get pure chirality. You can also see that the system is very sensitive to perturbations around this point. Any small deviation will kick you out of the exceptional point and will kick you out of the chiral state. So when we went to the lab, we got nearly pure chiral state, indeed, in the expected position, but the system is not sensitive at all. Small deviation of the complex potential didn't change much the chirality. And it turns out that the reason for this is the nonlinearity of the laser that actually pulls the system towards the exceptional point, but I won't go into this because I don't have time. And these are just images from the experiment. I won't go into this also. Let's go to the summary. So I introduced you to the Anyonic-PT symmetric laser. I showed you that we can generate chiral states with complex potential. And I didn't talk, I just showed an image of our recent effort of complex band structure engineering into where we would like to demonstrate some really cool physics by combining solid state physics in our laser systems. So, thank you. Questions?
So, the system is fully lased and it locks into something because of the nonlinearity, the lack of sensitivity. So if you were to reduce the gain, the overall gain, and come close to the threshold, would it become sharper?
No, it's not sensitive. The gain always, I don't know to explain you exactly why, but from other simulations, we saw that no matter how close you are to the threshold, the gain will always do some scheme with the loss to get us to the exceptional point, such that delta alpha minus delta G is the gain, is exactly at the exceptional point of the system. Like the tuning is fixed, you cannot change the tuning, but the gain is changed. I don't know how to explain you why, but it just happens.
Sounds like physics.
So thank you, Sagie.
Thank you.